Hello everyone, welcome to GRAMOLY YouTube channel. So today we are learning about arrows, which is a problem solving technique which is really useful. Previously we have used arrows just in warfare and other bad things, but today we are going to use them to solve problems, which is pretty ironic. But yeah, the idea is to represent iterated functions with arrows. So you might ask, how does it help to just visualize them? You will know really soon. So for example, if you have an iterated function, for example, this, to this, and you have f of 1 equals to f of 2 equals 3, f of 3 equals 1, f of 4 equals 5, and f of 5 equals 4. So if you draw arrows between the input and the output like this, f of 1, which is 2, and then note that f to the power k of I means that you apply the function k times on I. So it's not a big deal. It's just f of so on k times. And this is f of 1, which is f of 2, and which is, we know is 3. And then we have f of 1, which is f of 3, and it is just 1. So we just moved around a cycle and returned back to 1. So we can just draw it like this instead of just writing f 3 times. We can just directly draw the arrow from here. So this is a cycle with 3 elements. Similarly, you have 4 maps to f of 4, which is 5, and x squared 4 equals f of 5, which is 5, which is 4. So similarly, you can just draw an arrow directly. So this is also a cycle of length 2. You can have not only just cycles, like one thing to notice probably that if the range and domain is finite, then it's periodic. Basically, it means that after iterating it finitely many number of times, you return back to the same thing. But something like this can happen as well. Like if you have an injective function, then it's a bunch of chains and cycles. Say, for example, you have from R to R, you have f of n equals n plus 1. Or for simplicity's sake, we take it z to c. So first you have 1, then you have f of 1, which is 2, then you have f of 2, f of 1, which is f of 2, and this is 3, and it just goes on. It never returns to 1, which means this is a chain, it's an infinitely long chain because the set of integers is not finite. So this is the basic idea revolving around arrows. This might not seem too powerful yet, but we are going to display the technique in two problems here, which are decently hard. One is a P3 and one is an N6 from Elmo shortlist. So I think I will be able to convince you. Also, one idea is to one often a nice idea is to, if you see that you have a cycle, then you might want to consider the smallest n such that x returns to x. This is usually really helpful. We will look at how useful this is in the following in the problem. So the problem says prove that there is no real function f of x satisfying f of x equals x square minus 2 for all real numbers x. So this might seem like a normal functional equation, but it's actually not. It's actually very combinatorial. So I want you to try for a minute and I will be back. So first, the idea is to define the order of the function. So what is an order, you might ask? So order is, if you know some number theory, you might know that if something is mod p, and n is the smallest possible such number, then n is the order mod p of a. Similarly, we define order for functions. Like this is basically this. You want to define the smallest such n, such that f to the power n of x, which is f applied n times on x, returns to x. So one observation is that elements of order n are always divisible by n. Can you think of why? It's because the elements are in cycles of length n. So they must be divisible because say the length of the cycle is n. You have a lot of vertices. So this is the smallest possible. So the length is like 1, 2, 3, 4, 5. You can also extend it like mod 5. You can also say the length of the cycle. Actually, not the length of the cycle, but more like after five five times repeating the function, you return to the same value. And also, if you repeat the function 10 times, you also return to the value. So it must be multiple of 5, and here it must be multiple of n. So this is our observation. I think you should be convinced, and if you're not convinced yet, then just take an example and see that this is true. Now the idea is to look at f of f square minus x, which is f of x minus x. We know that f of x is x square minus 2. So this is this. And this is x square minus 2 whole square minus 2 minus x. Which if you factorize a little bit, which is not hard at all, you get this. So now this seems a little magical. You have these two terms here and also here. So how do you use it to get in probably a contradiction? Like you are assuming that such a function exists, but you need to find a contradiction which forces the function to not exist. Now note that this has roots half of -1 plus minus root 5, which is like the golden ratio or whatever. Now these two numbers satisfy. See, we defined order for the very reason, because we want to work with this. And defining an order is really, really useful, as you can see in this problem. And these two numbers satisfy this. I think we can all agree on this. And 4 is the order here because in f square of x minus x, these two terms don't occur. Whereas this x plus 1 and x minus 2 occur in f square x. And therefore, the order is 2 and not 4. Whereas these two numbers have order 4. But there are only two such numbers which have order 4, as you can see. But our observation was that elements, number of, actually, it should be number of elements of order. Sorry. So the number of elements of order n are divisible by n. But we have only two elements here. So this says that 4 must divide 2, which is really bizarre. And this is a contradiction. So we are done. So I hope you realize how powerful the idea is to consider the order of a function as defined. And if you have any difficulty understanding that number of elements of order n are divisible by n, I'm again saying that you should try it out. Try it example. I think it should help. Now we move to a slightly harder example, which is n6, and n6 are supposed to be hard, but don't be scared. Actually, it becomes much easier if you interpret it in an arrowish way. So this is proposed by Evan Chen. So you have this convoluted thing equals n. So it gives the order vibes, right? Because this maps to n. So for this to be true, what's the only restriction you can see? Can you guess the restriction? Like it's in the problem itself. The only restriction is that each element divides the length of its cycle. Like it must. We will prove it now. Don't worry. You can try some example maybe and like look at how it's working. It really helps. So can you guess the answer? It's m divides 2040 because of the reason I just mentioned. The only restriction is this, then the number of elements. So now our first claim is this: all saturated functions are bijective. But how do you prove it? First of all, note that it must be subjective because you can vary and however you want. You you can make this 1, 2, anything. So it's subjective, obviously. If you don't know what a surjective function is, it's a function if you have f maps to some set s to t, then f maps to every element in t. If a function is surjective, no element of t misses out. So we use a standard trick to prove injectivity of a function. So assume that for some a and b, f of a equals f of b equals x. Now the problem says that this implies that because we know that f of a equals x, so we can just simply represent it all in terms of x. Now similarly, we have for B, and both of them are the same. So it must happen that A equals B. So this is indeed injective. And since we prove that it is surjective and we know that this is injective, so we have the function is bijective. I hope this is clear. We are just substituting we are just substituting the x. It's nothing big deal. It's no big deal actually. So now note that you can take all these bad things which are really convoluted, modulo the order. Let the order of some m be g of m. Let the order be g of m. I will still remind you that an order is a number is a least number such that this thing is true. So we can take all these things mod of g of m because the length of this cycle will be g of m. We also have that g of m must divide 2014 and g of m also must divide f to the power f of m. Because in the problem we have that this thing is true, which means this is the length of the cycle. And since we know that g of n here is the order, it must divide. It must be divisible by g of n. I think this is clear. Now we have the key step of the problem. The idea is to take m equals g of m minus 1. So how do you motivate it first? So you might do this. Since you are trying a problem and it has iterated functions, the first thing you do is draw arrows. So you have this. So on, so on. We have f to the power g of m minus 1 of m, which maps to f to the power g of m of m, which is just m. So it makes sense to look at this element, right? Because it's the second last, it's the last element of the cycle. And it might give us some useful information. This is the idea behind looking at m equals g of m minus 1. So if you take this, you will get that this is true. I will leave the computation to you. It's really unhectic, so don't worry. Another advantage of teaching something is that you can just leave boring stuff to the people listening. So what does this mean? You guessed that right. It means that g of m divides f to the power m minus. Also note that all this f of stuff is in this cycle because it must be. It has every element f of some to the power something of m. Now consider the element which maps to this element. For example, I will draw the cycle again. You have this. Say somewhere around here. You have f to the power m minus 1 of m. Okay. Say here you have all these elements, and you have the element before the order here, which maps to. So now we look at this vertex. So what does this say? Yes, this means that the element which maps to f to the power m minus 1 of m also must be divisible by g of m. I will leave the computation to you. So inductively, we can say that every element of the cycle is divisible by g of m, because if you have this divisible by g of m, then the element which maps to this also divides g of m, is divisible by g of m. And this means g of m also divides m. And this just implies that m divides 2014. So we guess the answer was that it's m divides 2014, and we proved it. So what else do we have to finish the problem, to kill the problem? It's to find a construction such that the numbers which don't divide 2014 don't work. Can you find such a construction? It's not too hard. We can just consider. I think it's not the instructive part actually. The instructive part is this, where you consider the order first of all, and then have some divisibilities, and then you look at the last element of the cycle and see that g of m divides this too, and the thing that maps to f to the power m minus 1 of m also divides this, and inductively everything is divisible by g of m. This is the instructive part, and this is the thing that you should look into most. The construction is just this. You have f of m equals to m, f of 2m equals. Basically, you are considering every number which is a multiple of m till f of m square minus m plus m square, f of m square equals m, and you let all other inputs which are not divisible, all of the numbers, say I, to be identity. Identity basically means that f of x maps to x. So everything else maps to themselves. And we have a clear contradiction. You can check it yourself. So I think this should be fine. So let's summarize what we did. So first we looked at what arrows are and how they work. So sometimes you have chains, sometimes you have cycles, and in these two problems we just looked at cycles and didn't have any chains or something. In this problem, the idea was to look at f square of x minus x, because this is the definition of the order, and this is like polynomials and roots stuff which you might have learned in high school. So this is possibly a motivation behind this. And then you look, and the observation was that number of elements of order n are divisible by n. But we have that only two elements are have order 4. So 4 divides 2, which is a contradiction. And in the next problem, I think it's a really instructive problem. Sorry for spoiling it though. So first we guess the answer depending on the restriction of the order in 2014. And then we proved injectivity and proved bijectivity too. The motivation behind bijective was that a lot of times you have cycle being bijective because you have usually very less stuff to map to, and it's really a routine step to plug in stuff in FAs in general, and also in problems which involve arrows. So you proved injectivity, and then notice that you can take all this indices above mod of g of m, which is the order, and then you have this for divisibilities. You consider this because yeah, and then you prove that every element is divisible by g of m, so m is also divisible by g of m, and therefore m divides 2040. So yeah, we have solved 2 problems. And if you want more problems, then I have some stacked up. So first we have 2017 M3, which is a really cool problem. I really recommend you to try it. And then you have the US TST 2020 P5, which is also cool. It looks like a polynomial, but you have the arrow vibes, right? Because you have iterations. You have 2017 A3, and then a really hard problem, IMO 2015 P6. It has actually a few algebra steps later, but if you are able to do the arrow part, then it should be cool. And this is one of my favorite problems, which is 2012 A6. It is one of those problems which revolve around chains, and also don't worry, it doesn't really spoil the problem because it's a really minor part, and you will just find it easily that you have to work with chains on this problem. It's an A6, so it won't be too easy, but it's an amazing problem. And if you want even more problems, then Rohan Goyal has a really nice problem set, which we will link in the description. So thank you for watching.